speaker is Zhen Guo, spectroscopy variability of VVV eruptive variables YSOs.
So I'm Zhen from University of Hertfordshire. Today I'm going to show you our near-infrared spectroscopic results of those variable eruptive objects that Phil already showed us some light curves. So yeah, for those who are not really working on the primary sequence stage, so the evolution of primary sequence star can be divided into 4 stages, basically from class 0 to class 3. And the first 2 class 0 and class 1, we call it protostar because they can't actually be observed in optical, and they're embedded by their envelope and their disk. And then for the second part, class 2 and class 3 objects, we call it primary sequence or T-tower stars. They can actually show their variabilities in optical. So what we observe from the observed variability, we're actually using different wavelengths to trace different stages of stellar variability. For example, for protostars, we tend to use sub-millimeter or near-infrared observations because they're not seen in optical. And the variabilities on those kind of protostars may be dominated by the episodic accretion process. And then for later evolution stage, like class 2 and class 3 objects may be dominated by other kind of variabilities like the disk occultation, also the variable accretion also seen on those kind of objects. And that at the last is for reclined T-tower stars, they don't have very big disk or accretion event happen on the star. So what we see is all about the star spores rotating with the star itself. So different kinds of variabilities. And then today I'm going to focus on the near-infrared variable, to be honest, because we are in a VVV meeting. So all of those episodic accretion process help us to understand the luminosity problem, which is mentioned in the previous talk. So actually there is a 1 order of magnitude difference between the observation and the theoretical model for a class 1 object. The observed class 1 object is much fainter than the predicted from steady accretion model. To solve this, we proposed, Lee Hartman proposed this episodic accretion process that predicted a lot of accretion bursts in the protostar and T-tower star stage. And most of the eruptive event or the episodic accretion process is found in the protostar stage, which actually is in the near-infrared. So it's very crucial we use VV data with near-infrared survey to find all of those variable stars. And then those stars can drive a lot of problems from our for other like determination, stellar parameters, and also it affects the formation of planetesimals. And also to discuss this, to find more of those events, we can discuss the frequency of those events, and then to understand what's really going on during the star formation history. So yeah, you've seen this very famous light curves of a Fiori type stars, and the typical magnitude, the amplitude is about 5 magnitude in optical, and then the time scale of those events are really, really long. It's at least a decades long decaying. And then recently, by applying more whole sky survey, we can discover more and more of those objects. For example, last year, Lynn Hillenbrand and Carlos, they find an object from Gaia data that also fits this 5 magnitude rising. So another type of the star called EX-ORI star. They are like a little bit non-violent than the F-Fiori type. So their variation time scale is only about a year. So it just rise about like 3 to 5 magnitude and then just decay in a year. Those objects are confirmed that their variabilities come from the mass accretion process. So yeah, VV survey is very powerful. We found lots of variable stars from the VV survey, and then from Carlos's paper in 2017, we found at least 800 targets, well, 50% of them were YSOs. Well, by using the recent LISA Virac2 Lightcurve, we can find more and more of those objects. And then I'd like to show you this figure from Carlos's paper. You might not see it clearly. So basically at this side is protostar, and at the left side is the more evolved T-Tauri star. Now you can see most of the violent eruptive events are protostars and the class 1 objects, which we can use near-infrared follow-up to identify the mechanisms on those stars. So spectroscopic follow-up is very crucial for those objects because we need to confirm whether they are YSOs or not. And also we want to study the physical conditions around them, like how they accrete mass from their surrounding material. It is through a funnel, like a typical T-Tauri star, or just directly through the disk. Or rather, we can also study the inner disk structures of all of those objects if we see some extinctions and if we see some extra emission from the near infrared. At the last is we want to study the variation mechanism because the metric variability of the light curve can only tell us the two information. One of is the amplitude, one of is the time scale. But the real mechanism is actually hidden behind all of these light curves. I'm gonna go back to this point at the end of my talk. So yeah, this is kind of physical structures of the inner disk of accreting young stars. So there's a star, and then the innermost disk is about 0.05 AU away from the star. And then the material is truncated from this point and then accreted onto star following the magnetic field lines. And then from here, we can see that a lot of spectroscopic indicators of accretion, like the hydrogen recombination lines. In optical, we have very strong Balmer lines and Balmer jump. And then in near infrared, we can see Poisson beta or Berkeley gamma as indicators of mass accretion rate. And all of these lines has very broad line profiles as well. And then for the disk window jet, we can trace them by molecular hydrogen. And all of the molecular hydrogen has blue shifted, means that they are wind toward the outside. And also near infrared continuum can tell us some information from the innermost of the disk. And also the variation timescales of each spectroscopic indicators can roughly tell us the physical locations of those emission regions. So another different, very different type of object is FU Auris compared with those steady accretion scenario. In spectra of FU Auris type stars, you don't see any emission lines. What you're gonna see is H band here. It's like triangular shaped H band. It's caused by water absorption. And also in the beyond 2.3 micron, you see lots of CO absorption lines here. This is typical spectra of FU Auris. And then the physical structure of FU Auris is like they have inner star, and they have very hot accretion disk, can give you a very strong near infrared access. And also you have a huge envelope that create those water and CO absorptions. The formation, there are a lot of possibilities of the formation of FU Auris type stars still under debate. But one of my favorite is by Zhao Huanzhu, is predicted by gravitational instability that the disk can fragmented, and then part of the disk is accreted onto star suddenly and then create this violent event. So yeah, this is kind of our strategy plan for the spectroscopic follow-up. We started the follow-up from 2013 on Magellan telescope. In 2013 and 14, we observed the 33 targets, and we do spectroscopic classification from, this is published in Carlos' paper. And then in 2015, we kind of selected 14 young cell objects from the previous 2013 and 14 observation, and then we repeat observe those 14 young objects in 2 nights. So then we're going to study the short timescale variability of those 14 young objects in 2 nights, and also a long-term variability compared to the 2015 spectra and the previous 2013 and 14 spectra. We're going to see what's really going on those stars. Well, in 2017, we enlarge our samples, including more outburst targets and faders. We try to see what is the difference in those spectra. And also in 2019, we just finished this observation. We apply VLTX shooter observation for 15 high amplitude objects discovered in VVV Lightcurve. We try to build up a gallery for eruptive young objects, including their amplitude, their variation timescales, and also their morphologies of their light curves. Yeah. In this talk, I'm going to focus on the second part of our observations, is the 14 young objects that repeatedly observed in 2 nights. So yeah, before we go to the spectra, I want to show you the light curves of those objects. You might not really can see the details, but in general, for the first line, first layer here, you see all those light curves in pink and in blue. They are really smooth, right? So we call them brightening, or in outburst target that they have very big raising of their photometric magnitude. And then we observed the spectra from 2013 or 12 and or 14, and then we repeated in 2015. And then for the second layer is more complicated, but still you can find some regular things. So we call it descending objects, because between the 2 observation campaigns, we do see that the star become fainter during the 1 year or 2 years long interval. And then for the third layer, all of them are quite messy, because we can't really constrain the trend of the photometric behavior between 2 years, which means there might be meaningless if we just compare 2 years, because the variation timescale is much smaller than a year. It's just a sampling effect of the short timescale variability. And then to give a closer look for this, we call the third layer, we call mixed timescale variables. And for those variables, we find that they reached delta K larger than 0.5 magnitude in 100 days, so quite smaller than the typical spectroscopic interval, about a year. And also they reached 30% of their variability only in 30 days, so quite fast variabilities on those stars. So yeah, here is a nice example of the emission spectra of young stars. So this is V309. It's a very nice eruptive object. And then we can see many emission lines in the spectra, including those hydrogen, molecular hydrogen, and also Berkeley gamma with a broad line profile. And also sodium-1 is a doublet around 2.2 micron. And also the most important is the CO band emission that's beyond 2.3 micron. All of those can tell us many physics around those stars. And actually, we can define the ratio velocity of those lines. And then the ratio velocity of the star is defined by the CO emission band. And this method is applied in Carlos' paper in 2017 on many stars. So we can actually fit the CO line profile, emission profiles with the models, and then we define both the temperature and density of this area. And also we can define the ratio velocity of the star. And we also find that for molecular hydrogen emission, they always has a blue shift compared with other lines. It's about 100 kilometers per second, which means they are found in the outflow or jet. Yeah, here I summarize our 14 objects. Let's summarize the short timescale variability of the 14 objects. On the left-hand side is the molecular hydrogen emission. Basically, we can see that they're quite concentrate. And the y-axis is the difference in the ratio of the equivalent width of those lines in 2 nights. Basically, if it is around 1, it means it's not quite variable. And then we found the typical variation in between 2 nights is about 15%. So they do have a smaller variability, but not really strong in the timescale of days. And then on the other hand is the Brucker gamma emission, and they can change a lot in a timescale of 2 days or 1 day. So which means that those Brucker gamma emission actually generated very close to the star. And then when the star and the accretion stream is co-rotating, and we can cause this very big variations in a timescale of 1 day. But instead, this molecular hydrogen emission is formed a little bit outside in the disk, so you can't really see the variability in a timescale of 1 day. So, and also we can find some correlations between the CO band emission with the Brucker gamma emission, because both of them are thought as roughly indicators of a mass accretion process. And we found that they sort of have a correlation, but not really tight correlation, especially when we see when we discuss the variability over different years. For example, the purple one is V699. So this object, you can see they sort of have a close, very straight trend between 2 nights in 2015, showing here. But actually, if you trace this variability in 2014 and 13, we see that they have weird trend here, which means the CO and Brucker gamma is not close correlated on those targets on timescale of years. But it's reasonable because V699 is a mixed timescale variability star, which means the star changed their behavior within 100 days. So maybe the sampling effect over years and change this trend. But we still see very strong correlation between the CO emission, Brucker gamma emission in timescale of days. For example, like here and then from here to here, which means that CO emission also possibly locate very close to the star, along with the Brucker gamma emission, which means CO can survive within the Tercation radius of the inner edge of the disk, can extend it within the inner edge of the disk. It's quite fun to find out. And then we're going to discuss the years-long variability of those emission lines. Before that, I just want to show you the logic of this plot. So basically, I'm going to plot the variation of equivalent width and the variation of K-band continuum in this plot. As we know, the equivalent width actually the line flux divided the continuum flux. So if one of these changing, it can affect the equivalent width. For example, if the continuum is changing while the line itself is not changing, it's going to create an anti-correlation between the equivalent width and then the K-band continuum. They're going to locate it at the upper left and bottom right segments. And then if the both of the equivalent width and then the K-band continuum just arise together, which may correlate it with very strong accretion events that happen on the star, that they increase the mass accretion rate and then also the strains of the lines. And the third possibility is just there's actually nothing changed at the inner edge of the star. The variability is caused by extinction from outer disk, slightly outer disk, and then this can change the K-band magnitude, but not actually affect the measurement of the mass of the equivalent width. And also, I put a star here because the K-band magnitude we're using here is from the VVV Lightcurve, but we don't have exactly the same night have both spectroscopic observation and VVV Lightcurve. So here, the K-band magnitude we use is from synthetic K-band magnitude I using linear interpolation and then we apply that on the VV light curve. So it might have very big error bar, but not means that the measurement has big error bar. It just means that the star is variable very fast in a time scale of several days. So we can't actually constrain the K-band magnitude of those stars. So here is the result. On the left-hand side is the molecular hydrogen emission. In general, you can see that they all lie along this black line, which means that they have an anti-correlation between the K-band magnitude and also between the K-band magnitude and the equivalent width of the lines, which means that the molecular hydrogen is quite stable. The line itself is quite stable. But what causes this variability is come from the veiling of the continuum. And also on the other side, the Brucker gamma lines have a quite spread distribution on the plot, which means on the time scale of years, we can't draw a very simple conclusion of what happened on Brucker gamma, which means it's actually come from the variability of Brucker gamma. It's actually come from very short time scale. And if you just observe that over years long time scale, it's just a sampling effect of shorter time scale. It not actually makes sense. So, and then I'm going to show you a few individual objects. One of them is V8.5. We actually observed a molecular hydrogen bullet on this object. If you see in the middle, to plot here is in the first night in 2015 and the second night in 2015. We see both from both nights we have double Gaussian profiles of these lines, but actually you can see the low velocity component is quite stable compared between these 2 days, but the high velocity component changed a lot. And when we see it on the detector, we have a contour here. So by having the difference between 2 nights, we can actually see a very nice Gaussian shape, a high velocity component here, which means the star is shooting more molecular hydrogen in a 1 day time scale. And the velocity is about 100 kilometers per second. It's very fast. And then the second object is V631. This one is interesting because between 2 nights, even though the J-band and H-band spectra are not changing too much, we see that the K-band spectra, the continuum raised about 30%. What caused this variability in the time scale of 1 day? We think they might caused by a warp structure that's close to the inner edge of the star. And then the temperature of this disk warp is about 1000 K. So when it's co-rotated with the star, it can appear in our line of sight, and it can also move away from a line of sight. And then can cause this K-band continuum variation in the time scale of 1 day. And the third one is very interesting, is Furore-like spectra. So if you remember the Furore itself, it looks like this. So we have a triangular shape of H-band here caused by water absorption, and also the very strong CO absorptions beyond 2.3 micron. And this object actually arises in a very short time scale, about half a year, and then it decayed within the next few years on the VV light curve. And we actually capture the decaying stage of this event from 2013 to 14 to 15. You can see that along the decaying of the continuum, we can see the emission lines become stronger and stronger from 2013 to 14 to 15, which actually means that the molecular hydrogen emission is not actually affected by the enhancement of the K-band continuum. It stays constant. And when the K-band continuum becomes weaker and weaker, you actually see those lines. And also, with the decaying of the continuum, the CO absorption feature is become weaker and weaker, which means that it might close correlated with the K-band continuum. And also we see some kind of extra emission in 2014 here. So it's not traced the same shape of the continuum, and we can actually fit it by remove a 400K black body from the continuum, and then we can see that, oh, they keep the same. So maybe in 2014, there is a little bit warm outer disk or some structure that move in of line of sight and create this extra emission. And right now, we have VVX data. We can see that this star is go back to very faint stage again, and then it's reached around 16th magnitude. So if we apply another near infrared observation around here, so right now, and then we might see a very different spectra of this object. Maybe they have more emission lines, like the Brucker gamma and other emission lines that can tell us the termination of those very violent accretion process. So at the end, I want to show you one thing that V374, it changed its Brucker gamma emission to absorption in a time scale of 1 year. This is quite interesting. Maybe it's caused by the termination of mass accretion process, or maybe just caused by the geometric effect that you can't really see the accretion spot on the star. Maybe. And then, yeah. So at the last, I want to go back to one of my goal of this work is we want to use spectra to identify the variation mechanisms of those stars. Whether there are some objects that have similar light curve but have very different phenomena if you look at the spectra. So this is a good example, V662 and V665. These two objects have not exactly the same, but quite similar light curve between the 2014 and 15 observation season. You can see this one dropped about 0.6 magnitude, and this one dropped about 0.4 magnitude. And then the total variation scale is also the same. But when we take the spectra, we can see that in the 662 from 2014 to 2015, the emission lines just disappeared, which means the variation here might just caused by the termination or quenching of the mass accretion process. And then in this object, we see all the emission lines stay the same, exactly the same, even though the K-band continuum changed about 40%, which means the variability of these stars may actually come from the extinction, not any accretion process on it changing. So yeah, here is my summary. Episodic accretion process can help us to understand the luminosity problem, and also we need spectra to understand the mechanism behind the variation from the light curve, and also short time scale accretion process is commonly seen on Brucker gamma emissions. For the CO emissions is quite correlated with Brucker gamma on very short time scale, which also suggests they're very close in location of CO emission. And also the Wheeling effect from K-band continuum can cause a very large variation of the equivalent width of the molecular hydrogen, but it's not necessary that tell us the line itself is changing. Maybe the variation is just caused by the Wheeling effect. And at the last, the F-like object, V322, it has a deeper absorption feature when the star is brighter, and they have a stronger emission lines when the star is fainter. So thanks a lot.
In those objects that you observed a variation in the bracket gamma line, did you notice a change in the shape of the line? For example, in the relation between the width and the height? Or does the shape of the line remains more or less the same?
Mm-hmm. We do see some variability of the line profiles.
Okay.
And also they're in a very short time scale. Actually, this is also observed on many T-Tauri stars. The line profile is changing in a time scale of days to weeks because of they think that the mass is actually accreted through a funnel flow. It's through a tunnel onto the star. So when you actually see through the tunnel, you can see a very strong redshift accretion, redshift absorption on the lines. And then from our observation, we also see there one object might have this thing, but we can't really confirm because the signal to noise is not very good. But we do see something like that.
The object, like, I think 2 slides before this one, that one.
Yeah.
For this object, you observe a change from emission to absorption in bracket line.
Yes.
Is it my imagination or something similar happens with the CO band?
This
the
one
red
is
one,
weird.
I don't know if the CO could be considered an emission or.
Yeah, this one we don't see any CO emission because it's about 2.3 micron actually here.
It's probably more to the.
Yeah, so we can't really confirm that
Okay.
that's CO emission, but it's weak.
Magellan fire data is sometimes difficult to join the orders, and the order join happens to happen where the CO starts, so it creates some of these difficulties.
Yeah, so might have if you really zoom in around here, but not like a very strong one, like different, a few like peaks, not like that.